In previous math classes, you were introduced to the concept of absolute value. That's when there was a number located between two big, long absolute value bars. So up here in the upper left-hand corner of your screen, you see what would be described as the absolute value of 5. Absolute value is how far is it away from 0 on a number line. And 5 would be, here's 5, if we counted back, 1, 2, 3, 4, 5. It is 5 units from 0 on a number line, so we would say the absolute value of 5 is 5, because it's 5 units away from 0. Or the absolute value of -3. So here's -3. How far away is -3 from 0 on a number line? 1, 2, 3. So the absolute value of -3 is 3. Or how far is -½ away from 0 on a number line? So -½ is right here, and that's only a half of a step back to 0. So the absolute value of -½ is just 1/2. So many students remember absolute value to mean that it's just whatever that number is without the positive or the negative sign. And that would be pretty much true because absolute value is always going to be positive. And then maybe you were introduced to equations like the absolute value of x equals 6. Well, what values of x would have an absolute value that equals 6? Well, obviously 6 would. So x could equal 6, but x could also equal -6 because just like 6, -6 is also 1, 2, 3, 4, 5, 6 units away from 0 on a number line. So there was actually two answers to that. So what would that mean? The absolute value of 2, or absolute value of x equals 2, what would be the solutions for x? Well, it certainly could be 2, because 2 is 2 units away from 0 on a number line, but it is also -2. So it could be either one of those answers. X is equal to 2 or x equals -2. Today's lesson is really going to talk about how to find and graph absolute values of inequalities. So absolute value of x is less than 3. So let's just explore that for a second. What are some numbers that have an absolute value that is less than 3? Well, one of those numbers might be 2, because 2 is closer to 0 than the 3 is. Or it could be 1. Obviously 0, because 0, the absolute value of 0 is 0, and that's less than 3. What about a number like 4, though? Is the absolute value of 4 less than 3? No, because what is the absolute value of 4? The absolute value of 4 equals 4, and that is not less than 3. So we would not use 4 as one of the solutions. So we could just keep going less and less and less. So the absolute value of -1 is +1. The absolute value of -2 is +2. But let's say if we keep going to the left, let's say we got to -4. What is the absolute value of -4? The absolute value of -4 equals 4, and that is not less than 3. So actually the absolute value of -4 is not a solution to having an answer that is less than 3. So the numbers that we could use, including all these whole numbers and integers, we could also use all the fractions and the decimals in between. So like 1.5 or maybe -2/3. Looks like it's going to be all between the 3 and the -3. And that looks a whole lot like the and inequality that we had on the previous lesson. So this is not how you would actually solve and graph these types of problems. This is just to explore exactly why it works. But in order to solve an absolute value inequality, we would rewrite it as two inequalities. We could rewrite it as the absolute value of x. If it was less than 3, that means the x could be less than 3, and it could be greater than -3. In other words, between -3 and 3. So let's say we're going to solve the absolute value of m plus 2 is less than 11. The very first thing I'm going to do is to rewrite this as two separate, simple absolute values. I'm going to rewrite it as just like it's written without the absolute value bars. M plus 2 less than 11. Since it's a less than inequality with absolute value, I will use and. And then I'll write it again. M plus 2 could be greater than negative 11. And notice that when I changed it to negative 11, I flipped the sign. Very much like when you divide or multiply by a negative number, you flip the sign. With absolute values, when you change the second part to negative, you also flip the sign. So then I just solve both of those separately. So I subtract 2 from both sides on this one, and I get m less than 9, and subtract 2 from both sides on this one, and I get m greater than negative 13. So when I graph these, I'm going to put open circles on both of them because they are both without equal signs. So I'll put an open circle on the 9, and then I'll put an open circle on negative 13, which my number line isn't big enough, so I'll just make a couple of extra marks here. So negative 11, negative 12, negative 13. Put an open circle on that. And then, being an inequality, I'm going to shade in between. Remember that sometimes that and inequalities can be rewritten with them, both the inequalities pushed together. So that would be m less than 9, which is negative 13 is less than that. And again, notice that both the arrows are pointing to the left because just like a number line, the smaller numbers are to the left. So the smaller number, the negative 13 is to the left. It's less than m, less than 9. Either one of these answers, whether you write it like this or like this, would be acceptable, but be aware that on multiple choice tests, many times they write it like that. So be aware that you may have to know both anyway. Let's try the next one. Its absolute value of 2c minus 5 is less than or equal to 3. So the very first thing I'm going to do is rewrite it as 2c minus 5 is less than or equal to 3. Again, just like it is without absolute value bars. The word and. Then 2c minus 5 is greater than or equal to. So I flip that sign and I change the sign of the number that it is greater than or equal to negative 3. Then I solve them both separately. So I add 5 to both sides on this one, and I get 2c is less than or equal to 8. Divide by 2. C is less than or equal to 4. And add 5 to both of them on this one. So 2c is greater than or equal to 2. Divided by 2. C is greater than or equal to 1. So this time they're both less than or equal to, greater than or equal to, so I will put dots on those numbers. I'll put a dot on the 4. I'll put a dot on the positive 1. So I'm shading less than 4 and greater than 1, in other words, between the 4 and the 1. So those are less than absolute value inequalities. Less than absolute value inequalities, we will use and. Let's explore what a greater than absolute value inequality might look like. So what are some numbers with an absolute value that is greater than 4? So that would be numbers like 5, 6, 7, 8.5. We don't want to neglect our fractions. 9.2, or our decimals, or anything that is larger than 10 that's not on this number line. So are those the only numbers that have absolute values greater than 4? Well, what about a number like negative 5? What is its absolute value? Is it greater than 4? It sure is, because what is the absolute value of negative 5? Well, the absolute value of negative 5 is 5, and that is a number that's larger than 4. So negative 5 actually has an absolute value that's greater than 4, as does negative 6, because the absolute value of negative 6 is 6, and that's greater than 4. and negative 7 and negative 9.5 and all those fractions and decimals and numbers to the left of negative 10. They all have absolute values that are greater than 4. But so what doesn't have an absolute value greater than 4? Well, numbers like 3. 3 does not, because the absolute value of 3 is 3, and that's not greater than 4. Or numbers like negative 2 do not, because the absolute value of negative 2 is just 2, and that's not greater than 4. So when I do some shading on these, notice that the shading is to the outside, and that looks suspiciously like an OR inequality. And we can use an OR inequality when it uses a greater than or a greater than and equal to symbol. So one way to remember whether to use and or is when it uses a less than symbol, we're going to use and. When it uses a greater than symbol, we're going to use or. So it's like less than and, greater or. Maybe a little stretch, but hopefully it helps you remember which one to use. So our absolute value of r minus 3 is greater than or equal to 5. So I am going to rewrite this. It'll be r minus 3 greater than or equal to 5, just like it's written without the absolute value bars. Since the original problem has a greater symbol in it, we're going to use or. R minus 3, flip the sign to point the other direction and make it negative. And then we solve both of those separately. So r is greater than or equal to 8, or, and on this side we'll add 3 again, r is less than or equal to negative 2. When we graph those, we'll put dots on both sides because they are equal to. So dot on 8, we're shading to the right of 8. To the right of that is larger than 8. And we will also put a dot on negative 2 and the numbers to the left of negative 2. So greater is or, and that gets shaded to the outside. So let's try one more. The absolute value of 2k plus 1 is greater than 7. So we're going to rewrite these. It'll be 2k plus 1 greater than 7, or 2k plus 1 less than negative 7. Then we solve them separately. So I'll subtract 1 from both sides. That gives me 2k is greater than positive 6. Divide by 2. So k is greater than 3, or same steps on the other one. Negative 7 minus 1 is negative 8. Divide by 2. Get k is less than negative 4. So we're going to put open circles on both of these. Shade to the right of 3 for k is greater than 3. And then to the left of negative 4 for k is less than negative 4. In other words, to the outside of the 3 and the negative 4.